Thank you very much, Michael. I thank the organizers for inviting me to this wonderful place and meet wonderful people and a wonderful subject. So we'll climb the stairs together. So I'm very happy that Professor Mukunda and Rajaram Nityananda are around. So I have to acknowledge them for removing fear of gauge fields and EMUs. When I learned MSc, we use vector notation for electric field, and we use curl for cross products like this. Then things like EMU are somewhat scary. Then we have groups. As a solid state physicist, I know translation, lattice symmetries and point groups, and you can take a cube and rotate it and see the groups there. But when people talk about SU2 or SU3, it became very scary. A lot of generators and indices, colors, and so on. So these fears were removed by Professor Mukunda, because I was very fortunate that you may not remember, during my PhD days and a little later, I attended 4 of his courses. It may have been a waste on me, but still I picked up something. Classical dynamics, continuous groups, and then differential equation, and then about Dirac constraint theory and so on. So it was a very eclectic period at IISc Bangalore. So coming from a solid state physics background, my fear for SU3 and so on slightly disappeared. So I have to thank you. And then Professor Rajaram, he gave us a lot of confidence about quantum field theory. He said, he introduced quantum mechanics through path integrals and again removed the fear of quantum field theory. And Rajaram Nityananda is always with us. Whenever you had any doubt, he clarified it. He will come again later. So my collaborators over years, where we have done some work on emergent gauge fields in quantum matter. And this Science and Engineering Research Board, DST India, for support after superannuation, similarly Perimeter Institute for a wonderful position there, and also recently IIT Madras. Okay. So we all know about Berry connection and the Berry phase. We have this sphere, we have heard about it. Now let me tell you about my Berry connection. So again, I have to bring in Rajaram Nityananda, an Indian sub-science. I think it was way back in 1976. I thought it was 73. Then I checked with Berry's website, it is 76. So he was visiting and giving a series of wonderful lectures. So Rajaram Nityananda and myself attended all the lectures. And at the end of the talk, I will sit with Rajaram. He will explain to me what Michael did in the class. Quantum chaos, wave singularities, caustics, and a variety of wonderful topics. It was before the Berry phase, 76. Then he may not remember, I visited Bristol because I was spending some time at ICTP, and then ICTP was good enough to send us to other places within Europe. So I visited Professor Paul Butcher and then I went and visited Michael in 1978. That was long back. That was in University of Bristol, and then we met in IMSc. Then Indian International Institute for Physics at Natal in Brazil, which is an offshoot of International Center for Condensed Matter Physics, which was in Brasilia. Then now in Bangalore. So it's a closed circuit. So I have learned a lot and picked up non-zero Berry phase. Thank you, Michael. So this is my Berry connection. So yesterday's talk was this. I missed Professor Mukunda's talk for a foggy reason. I woke up at 4 o'clock in the morning to catch the 6 o'clock flight. So I did catch the flight, didn't miss it. Then the flight came up to Bangalore. It was a propeller flight, so it was no automatic control, so they could not land because of the fog condition. So they roamed around for 40 minutes, and then went back to Chennai and landed there, where there was no fog. Then after an hour started, so I missed Professor Mukunda's lecture. So I have never visited Bangalore twice in my life on the same day. So that was yesterday. So I look forward to the video of his talk. Then Michael Berry gave a wonderful talk about geometric phases and the separation of the world. Then Rajaram about geometrical and topological view of classical physics. So it was a beautiful session. Today it will be, my part will be a lot of condensed matter mess. It won't be very neat and so on, but let's see. Then today's talk, I'm going to talk about emergent gauge fields and in quantum matter. Then Vijay Shanai will talk about phases to phases, a brief view of quantum matter, touching topological aspects. So will Sumati, topological phases of quantum matter. So there may be some overlap, but there is no harm in having overlap. It's like Michael said, that it's different perspective. Okay, so this is roughly what I'm going to do. I will talk about low energy physics and Hilbert space projection or truncation, which leads to very interesting rich physics compared to unprojected simple Hilbert spaces. Then talk about dynamically generated gauge fields and then try to understand it through some solvable models. This is going to be my plan. Elementary gauge fields already started with quantum electrodynamics, Maxwell's theory, that's a UN gauge theory. Then a triumph in high energy physics, setting up of the standard model involved SU3 gauge fields, SU2 and UN gauge theory. While they were all, in some sense elementary, people wanted to bring them as emergent. In fact, there's an old work by Kaluza-Klein theory, very beautiful. You start with 5-dimensional gauge theory and curl up one direction, and that becomes U1 gauge theory, electromagnetism. These days, string theory friends talk about emergent gauge theory from a very different perspective. So that's beyond the standard model. And there is one very pretty work by my friend Amati from CISA now and Amati Testa model, emergent SU3 gauge fields. This is in some spirit similar to what happens in constrained systems in condensed matter physics. So here the idea is the following. You start with quarks and leptons and then only U1 electromagnetic field. Don't bring in SU3 gauge fields, but demand that quarks do not appear in the physical sector or in the low energy sector. So you put it like a constraint saying that local color singlet constraint, only color singlet objects can be seen. So this is added by hand. Then you can do path integrals and find out that SU3 gauge fields emerge. They also become dynamical through radiative corrections. So this is a very beautiful attempt called Amati Testa model. So this is one place where emergent gauge field appear in a very beautiful way in the context of high energy physics through path integral. Yeah. So you have so many quarks with color indices. So the Lagrangian multipliers become the gauge fields, and then they are position and time dependent. Then time derivatives, everything emerge. It's a very beautiful work. In fact, once when I was talking with Professor Rajasekaran about our gauge theory work, he said Amati and Testa have done very similar thing long back. So he brought that to my attention. Yeah, correct, exactly. He also, so I should have, so this was, I think, an elaboration of Amati-Tesla model. That's how, maybe I should, sorry, I forgot about that paper in Pramana. Yeah. But it was Rajaseran who told me. So, now, okay, this is the kind of bird's eye view. It's like, suppose somebody goes on a tour in Bangalore, so you have a half a day tour. So what do? You take some big bus, so there will be the person who explains, that is Vidhan Sauda, then after some time that is Kabban Park, then after some time that's Tata Institute, things like that. So that's what I'm going to do today, next 1 hour. So it's amazing that gauge fields appeared in different places, elasticity theory and gauge theory of dislocations, and 2D theory of melting and liquid crystals. I will explain them in classical spin-nice systems and emergent gauge fields. Very beautiful developments of things like classical monopoles and thermodynamics of monopoles and electric charges in real physical systems, even though the Maxwell's monopole doesn't exist. Superfluid superconductors, gauge fields, vortex duality, then topological insulators, gauge fields in K space. I think Sumati and Vijay will talk about it in great detail. Then integer and fractional quantum Hall effect, where Chern-Simons gauge theory comes, Majorana fermions, Fibonacci anions, and a variety of things. Then quantum spin liquids in Mott insulators, emergent T1, SU2, C2 gauge fields, pseudo fermions, Majorana fermions. Then I will spend some time on some models like Kitaev models and also quantum dimer model to explain what is topological degeneracy and some Chern-Simons topological field theory behind it, and so on. So this is the bird's eye view of what I wish to share with you, some perspectives about this. So just about condensed matter physics, we start with electron, nuclei, photons, atoms, molecules, solids. Photons are the even gauge fields. And quasi-particles appear when you have a Fermi sea of electrons. So they are the electron and hole quasi-particles. Then we have phonons, magnons, polaron, polaritron, exciton, plasma, bosonic emergent excitations. And we have very well established Fermi liquid theory of metals, BCS theory of superconductor, theory of charge density, spin density, band insulators, topological insulators, ferroelectrics, Bose superfluids. So in some sense, in all these systems, things do get renormalized, but interaction at some scale become irrelevant after renormalization. So you have some new beautiful correspondence to some non-interacting physics with renormalized parameters. Things are not that simple when we come to strongly correlated electron systems. Very popular ones are these Mott insulators and quantum magnets, quantum Hall systems. These days, optical lattices of cold atoms. It's an amazing laboratory. Now, you have any model that you like, in principle it can be realized in optical lattices. Now, people are like synthetic gauge fields, and a variety of things can be done with cold atoms. Amazing quantum physics. Now, here these are all very strongly constrained systems. It's like crowded. I know the place in Chennai, near T Nagar. It's a very crowded area. So you go there, you lose your spin. For example, you lose your purse, spin charge decoupling. So I think in Bangalore also there are places like that. You get decoupled from your possession. So you have frozen charge dynamics. You cannot move, but some of your objects move. So spin dynamics. Electrons lose their identity in a crowded environment. What is remarkable is remarkable collective quantum effects emerge in these systems. So this is what we will talk in the next rest of the time. So the task is low energy description and elementary excitations, identify relevant degree of freedom, find effective Hamiltonians. Now there is a variety of them. In fact, if you look at condensed matter archive these days, Every day there are 10 papers on 10 different 2D materials, just not graphene alone. Tungsten diselenide, niobium ditelluride, and all kinds of beautiful things. And there is fight for modeling, 2-3 models for every system. So there is a variety of them, new experiments, cold atoms. So the real challenge is to understand, conceptualize, find correct models, find solutions, classify vacuum phases, explain experimental anomalies, and make predictions. It's a very tough job for condensed matter physicists. When you start looking at experimental results, sometimes just resistivity or some frequency dependent conductivity or some dielectric constant, you have to go deeply into the system and do all these things from microscopics. Of course, there is always these days ab initio power. People say that anything can be done from ab initio, but then there are problems there. You can get something, but low energy physics you will often miss. So it's a big, interesting game and challenges. So now we are interested in the structure of ground state vacuum. We are familiar with vacuum of electromagnetic, just vacuum without fermions. It's a very simple collection of oscillators. But then when you go to SU3 gauge theory, you have so-called spaghetti vacuum. That is, there are color flux lines which fill the vacuum and they are quantum fluctuating. So description becomes very complicated. It's a strong coupling theory. That's why you have confinement and so on. Now, in a similar way in condensed matter systems, in these many new systems that are being investigated, conventional long-range order is absent. Like if you take a ferromagnet, you have spin, which keeps the long-range orientational correlation. You have a charge density wave, you have density waves, and so on. Or in a superconductor, you have the phase order. But so they are called Landau type of long-range order. It can be described in terms of some Landau order parameter, which can be made local, and you can develop phenomenological theory. Now you have, on top of that, so-called quantum order, which are something to do with topological entanglement and a variety of beautiful things. So there are topological gauge field theories and Chern-Simons theory, and unusual excitations, edge excitations. All these things are part of the vacuum and its edges. So we want descriptions for them. And then, as I said, the objects, namely constituent objects, are very different from what you see at low energy scales. Quasi-particles do not have the same quantum number as the constituent particles. Beautiful and very deeply understood example is Laughlin's fractional quantum Hall states, where constituent objects are electrons carrying charge plus minus E. Then you can create a so-called sharp excitation carrying charge 1/3 of E. And then in high temperature superconductors and other spin liquid systems, you can have spin carrying excitations or charge carrying excitations. So many interesting things happen here. Not only that, why I'm saying all this is due to the emergent gauge fields in the background. And most of these elementary excitations are strongly correlated, some are quantized vortices of some underlying spin or charge quantum fluid, topological in nature. And you have unusual statistics, very beautiful idea of something called exclusion statistics. Now, we know Pauli exclusion principle. Now, if there is a particle in a quantum state, if it is a fermion, it will not accommodate another particle, another fermion with the same quantum state. Like two electrons with parallel spin, you cannot put them in the same plane wave state. Now, Haldane found out that in many of these systems, in strongly interacting systems, the exclusion can be partly true. That is, I can accommodate half of a particle, for example. So you have generalized Pauli exclusion principle to exclusion statistics, where exclusion statistics can be like 3/2 rather than 1. So these things happen, and in fact, again, one can trace some of them, these things, to emergent gauge fields. Similarly, exchange statistics become very different. There are anions, that is, if I exchange two particles, I don't get -1 or +1. I get some unusual pi by 2, for example, or some theta. So variety of things happens, and also non-abelian anions, Majorana fermion, and fractons. I will discuss some of these things later. Again, due to gauge fields. In many of them, it is two-dimensional, 1 and 2-dimensional. There are some examples in 3-dimension also. So yeah, thanks for reminding. So all these very esoteric things are very easily happening in 1 and 2-dimension. Okay, so this is, just gauge fields. Non-abelian gauge field. Okay, let me start with this. So condensed matter physics is a place where defects become beautiful and give strength to materials. We all know this. If you talk to metallurgy colleagues, they say that if you look at the aircraft, when it lands, I was recently giving a talk somewhere that the largest aircraft in the world is something called Mira. It's a MY, it's a Russian cargo. It's like 300 tons, like 300 cars load. So imagine it landing, and that shaft has to support such a big shock. So if you go into the material science, it involves a lot of nanocomposites and strength coming from grain boundaries and dislocation loops and so on. So defects help a lot. So beautiful mathematics, physics, and phenomena follows. So a simple example is this edge dislocation in a simple cubic lattice. Where is gauge theory? Sorry. So it's very remarkable that before Maxwell's theory came, continuum theory of elasticity existed. But things like gauge field and gauge invariance came later in the field of continuum elasticity. So theory of defects and use of gauge fields followed much later. And long back I have read this book by Kleinert, Gauge Fields in Condensed Matter. Very nice sections are there. So while searching, I found that he has put this book in his website. You can freely download it and use it for personal purposes. So it's a very, Balsakumar, many of you may know, is a very dear friend of us, and he's no more. He passed away last year. So he gave, in fact, a series of talks at MadScience on gauge theory of defects in elastic continuum. There's a very nice 40-50 page article, Balsa and Sahu, in Bulletin of Material Science, a journal run by Indian Academy of Sciences. In fact, you can get it freely from the Academy website. So the principle of local gauge invariance enables us to introduce topological defects in an elastic continuum in a fundamental manner. One novel feature of this approach is that defects have a core. Apparently, in the theory of defects, particularly when you deal with continuum elasticity theory, there are issues about core energies and so on. So many of these things can be taken care of. This removes the divergence of the stress field at the origin and so on. So he has some very nice sections on fiber bundles, how, we know when we talk about materials, bundles and so on, that we had pictures of them. But here fiber bundles, mathematical bundles come and help you to understand some of these material bundles. And very remarkable recent developments. I had a very nice talk about this by Vijay Shanayal last month at ICTS about fractons. So, okay, I will point out what fractons are a little later through some very simple models. But the idea is that there are models now inspired by some quantum spin models which supports excitations. For example, it can be an excitation that can move only one direction. It cannot move in the transverse direction. Similarly, there can be excitations in the plane which cannot move up and down. They can only rotate and so on. So they occur in local models with local Hamiltonians containing spins in a very beautiful way. And recently there are beautiful developments that a continuum theory of such models actually have connected to elasticity theories. They're called Fracton-Elasticity Duality, paper by Predko and Zadzowski. So hopefully Vijay and I will, very beautiful connections. I will not go into the detail. I wanted to point this out. And then there was a very nice seminar at Mad Science last month. Shreya Pai, some of you know her. She was an undergraduate student at IISc. I believe she did a project with Agarwal, who is sitting somewhere. Yeah. So she gave a beautiful talk about this fractons and the 3D elasticity theory, where fourth rank tensor gauge theory comes in a very natural way. And phonons are connected to gapless gauge modes. And disclinations are like line charges and so on. Very beautiful developments happening just in recent times. And there's a very nice review article by Nand Kishore and company in Annual Reviews of Condensed Matter Physics. So I will come back to this when I introduce the model of fracton in terms of spins, which is a very simple model, but still containing very rich physics. So one of the classical success of gauge theory in the context of condensed matter physics is superconductors coupled to electromagnetic field. The Goldstone mode or photon acquires mass, becomes plasma. It's called Anderson-Higgs mechanism of mass generation, which had very important implications in elementary particle physics. Even more, superfluid helium in 2 dimension and has a very beautiful duality. Goldstone mode becomes U1 gauge field, quantized vertices becomes magnetic charges. And then if you take like liquid helium-4 and apply pressure in its superfluid state, at some point it will lose superfluidity, it will become a solid crystal. So this is related to Higgs phenomena and so on, which can be described in terms of Bose-Hubbard model. I just wanted to point out again recent developments which are remarkable, very interesting. So this involves the idea of duality. Emergent gauge fields can be connected to constituent object through dual transformations. There is a very classic paper by Mikhail Peskin, then a very important paper by Chandan Dasgupta and Halperin. Chandan is here. Phase transition, a lattice model of superconductivity. That has grown actually into a web now. This is a very interesting paper by Nathan Steinberg, Senthil, Wang, and Witten, a duality of web in 2 + 1 dimensions and condensed matter physics. So it's very refreshing to see condensed matter physics in the hands of condensed matter physicists and string theories creating a web. And very exciting things. I wish I understand all of them. I understand only the part of the web. But some people say that don't get trapped in the web. String theory web. Okay. So very fascinating developments are taking place. Many of them are emergent gauge fields and duality. Okay, now let me come to the real problem that condensed matter physicists face the last 30, 40 years in terms of trying to get good quantitative understanding through simple models. Lots of things are left still ununderstood. The problem is the following. So Mott asked the following question. Suppose I have a collection of hydrogen atom forming, let's say, a cubic lattice. So the atom wave functions overlap. So the lattice parameters are like comparable to Bohr radius. Then the wave functions overlap, and it's energetically advantageous for me to delocalize and form block state. And I have 1 electron per 1s orbital. So I will have essentially a band, a 1s band with a gap with the excited bands above. So this band will be half filled. So it's a very textbook situation of a simple metal which is half filled. So you can have a Brillouin zone and you have a simple Fermi surface. Now, Mott asked the following question. Suppose you expand the metal. Make the lattice parameter larger than Bohr radius. In fact, you can do this in real situations. Take, for example, copper atom and insert oxygen. You get CuO and you get a Mott insulator. So he said a stage will come in which it is not energetically advantageous in the ground state for an electron to leave its home and to form a block state. So it will rather stay home and maybe do some quantum fluctuations. Then in that case, since there is only one electron from each hydrogen atom, there is a spin degree of freedom, which is essentially free. So this is a Martin insulator. You have very soft spins, but charges are very hard, they cannot move. So you can do a caricature and call it upper Hubbard band, that if you want to really create a charge or move a charge and create a current carrying state, you'll have to pluck out an electron from its home and then put it on top of somebody else who may not like him. So that's called Hubbard U. So there is the repulsive energy. If that energy is larger than the bandwidth, electrons will stay home and do quantum fluctuation. This state is very easily described in words, the way that I said. But to do a mathematics of this and do a many-body theory is very hard. It depends on details of the nature of the lattice. And the end is not a simple direct product state. It's a highly entangled state or sums of related determinants and so on. So this is what we want to do, and we will see very quickly that gauge fields emerge in this kind of constrained situation in a very natural way and with a great variety. So what do they do? So I have highly expanded situations in which electrons don't communicate with each other, but when I bring them close by, since they are quantum mechanical, there will be always virtual transitions. For example, if we take an upspin and downspin electron to neighboring sites, there is a small amplitude for it to jump, and I'm looking for a pointer. Okay, I will point with my finger. So there is a small amplitude for this electron to jump, create a large energy configuration. So you have a virtual process. In this process, you do gain some energy, delocalization energy. So it's very interesting that this is possible if the spins are anti-parallel or if there is some singlet component. If we take two spins which are parallel, then Pauli will block it. So this is called Pauli blocking. So Pauli principle and Coulomb repulsion distinguishes spin triplet state and spin singlet state. So this put together gives us the famous Heisenberg exchange, effective Hamiltonian, in this Martin insulating state. So L charges are not free to move. So the charges do not appear in low energy physics, whereas spins appear as this in terms of this exchange integral and then exchange term. So this is very beautiful. So I have reduced the problem of freely moving electron in a constrained situation to just spin degree of freedom. So I have truncated the Hilbert space. So this is going to lead to very interesting, rich consequences. So this is summarized in the very beautiful, well-known model called Hubbard Model. It was discovered by several people, Kanamori, Gutzwiller, Anderson, and Hubbard, and others probably. So this model is exactly, sorry, this is Lieb and V, not V, it's Wu. Sorry, excuse me. Yeah, so the charge distribution will be, suppose you do an X-ray scattering, you will see charges around the atom. But we cannot say how the charges are correlated. In fact, it's a very important point. In the famous density functional theory, which focuses only on local charges, you cannot bring out correlation. But you can go slightly beyond that, something called electron localization function. That can tell about correlation between charges with opposite spin. Yeah. So if we just look at the density, there is no way of finding out if something is a Martin insulator or not. But you'll have to go beyond in terms of some two-particle correlation. Have I answered your question? Okay. So this is called Hubbard model, solved by Lieb and Wu. In one day, it's a beautiful model by using Bhattacharjee's technique. It gives extremely non-trivial result. You know, I call it as a very unfriendly solution because the solution is there, but you can't see the physics that easily. We will see a friendly solution later. That's why I call it. All the Bhattacharjees, everything, but the physics is extremely rich. Then, when the U becomes very large, when you have half filling, like the case of collection of hydrogen atom forming a lattice, you have no charge degree of freedom, you have so-called Heisenberg model. But suppose I come from outside and remove some charges by hand. For example, it happens in lanthanum copper oxide. This is supposed to be a Mott insulator where there is a plane. Every copper contains essentially one d hole, or you can call it as one electron. Now, when I come here and replace some of the lanthanum by barium, whose valence is 2, oxygen grabs the electron from copper, and you are creating some copper containing no hole or 2 holes. So, in other words, in this language, what happens is you have some spins missing, so this electron can easily hop locally, but of course it cannot hop to the next site because there is another electron. So, you have a constrained dynamics of the so-called doped holes, and that is described by this called TJ model. So, it's an effective model of Hubbard model for large U. Now, this contains the local physics of whatever I called as exchange interaction. Then there is a constraint here that as you use this Hamiltonian, you better be careful. At no time 2 electrons can sit on top of each other with opposite spin. That has been projected out. So this is again a very hard problem to solve. We have solved it using mean field theory and various tricks, which gives you some beautiful global picture. But when you want to do it in detail, you have to go to variational theories, and numerically it becomes extremely complicated. Even quantum Monte Carlo and everything is very hard. So a lot of activity is continuing to be there. So now we will see that we can extract some physics from simple mean field theory, and also going beyond the spirit of gauge theory will come here. Okay, so when we were encountered with this in this paper with Anderson, what we did was sorry for this. So there is some mismatch when I come here. So spin operators here can be expressed in terms of the underlying electron operator. And then you can write this spin operator in terms of electron operators, in terms of these bond singlets and so on, and do what we will call as Hartree-Fock theory. Just you have 2-body interaction alone, no 1-body term, kinetic energy term. So factorize it and solve some theory, and you get some very beautiful solution, which is agreeing with what is seen experimentally, but there is no way of justifying this mean field theory. As often, mean field theories do not have justification except from experiments. Then you try to go beyond mean field theory and see corrections and so on. Here, we did a very cavalier thing that we went beyond the physical Hilbert space and did mean field theory. So the mean field theory is not even respected by variational principles. But still interesting results were there. So then we wanted to go slightly beyond, because it's like, mean field theory is a first attempt, like when child is walking, it's limping and then falling down and so on, but then you want to go beyond that. This is where this local physics gave us some clue to what is going on. So let me spend some time on this, how gauge theory comes. In fact, I will try to point out in this context, gauge theory or gauge fields are Hartree-Fock vector potential in the following sense. So I have a situation like this. Now this electron cannot move on its own, this electron cannot move, but in higher order we have shown there is a possibility. So what has happened? So in a sense, there is one electron which has gone from here to here, and another electron gone from. So there is a backflow. So at the end of the day, I have 1 electron per site. The spin configuration has changed. So there is some kind of emergent local number conservation. That is, the number was 1 here. There is a virtual state, we will forget about it. We have integrated it out. So I am getting again occupancy 1. So that is a very simple emergent local conservation. Consequently, there is a local gauge invariance. Now, if I write it not in spin language, in terms of electron language, it looks like this. Believe me that the S dot S term can be rewritten like this. plus Hermitian conjugate. And there is a summation over sigma. This term essentially says that if one electron moves this way, other that moves back that way. So this is a very funny two-body interaction, which is not local. So this electron moves this way, so it looks like a current-current interaction, which immediately smells like some gauge field. So in other words, I can take this and do some very simple Hartree-Fock factorization. So what I will get is I will get some chi-ij, chi-12 plus Hermitian conjugate. So it's an approximation. Now this is essentially telling about the background charge that is moving, and it could carry some phase information because I have not fixed what is the value of this. So in principle, this could be a complex. Now that immediately reminds us that it could be written as, this again reminds us of famous Piles factor. So I have got a Hartree-Fock potential term, Hartree-Fock average, which can have a phase which depends on the site 1 and 2. I can formally write it as A dot dl. So this is the observation that we made. So what is actually happening is the problem of mean field theory that we did, where we allowed everybody to move around, we did not respect the local constraint, can be taken care of if we recognize that as we do the problem, there is a local conservation. In other words, if I look at this Hamiltonian, you can take Ci sigma and replace it by e to the power of I theta I. So the Hamiltonian remains invariant because theta I will appear as minus theta in the next term, so everything will go away. So there is a local U1 gauge invariance. And now that means the Hartree-Fock potential that I have here can be thought of as a link field which carries some dynamical theta ij. So this was a very simple observation, and we elaborated in a paper. We had a slightly different representation, please forget about that. So at the end of the day, what you have is you have an effective action in terms of some link variable which has local gauge invariance. Then we also pointed out that this, in order to implement, if you start talking about gauge theory, you'll have to talk in terms of so-called Wilson loops, which are observables. So as far as we remember, this is the first time in which this kind of gauge fields appeared, and then Wilson loops in condensed matter context came. So this resulted in a lot of help from other friends. Okay, so this is, so let me give you some of the meaning of this gauge. Suppose you say that there is a gauge transformation like this, and then you have some link field. Then if you take a small Wilson loop, smallest Wilson loop corresponding to a triangle, then you get a very beautiful connection of that operator. That is, if you take this tau 1, 2, tau 2, 3, if you take the imaginary part of that, it is essentially S1, 2. This is called vector chirality. This term tells you how 3 spins quantum fluctuate. What is the handedness? If this is 1, for example, they are left-handed. If it is -1, it's right-handed. Yeah. Tau is this, sorry, I should have told. So I call this tau 1, 2 as, so the hopping operator. So that's like a link variable. And if I take the product around, it's amazing that I did not put any spin information. But at the end of the day, when you do it, you find that if a spin circulates, and if another compensating electron also circulates, you get some information about the nature of quantum fluctuations of the 3 spins through this operator. So this is a Wilson loop, which is gauge invariant when you write it in this language. By imaginary part, you mean the expectation values imaginary part? Yeah, No, this is an identity. Okay, so you are asking why imaginary part? Exactly, operator. And then, because write this in terms of electron creation annihilation operator. In fact, to be very precise, sorry, I should say that clockwise, counterclockwise, which is related to the imaginary part. That is 1, 3. And then multiply by an I, you will get something like this. So it's interesting. So what is happening is, the meaning of the Hartree-Fock field is, the Hartree-Fock field here, the vector potential, has some information about the spin Berry phase. So as the spin is precessing, it is carrying some Berry phase, and here it is expressed in terms of this chirality. So this is a thing. Now, in fact, I will. Sorry, dot. Thank you for. So that's why we need old friends. So the cross between us is removed. S dot S cross, yes. Yeah, thank you. Okay, now in fact, many of these things will become beautifully clear through a solvable model given by Kitaev. So all the mess will hopefully. Okay, now in other contexts, nonlinear sigma model, like same spin problem, if you go to order parameter description in terms of sublattice magnetization, which is unity, whose magnitude is unity, then you have this Lagrangian for, this is a famous nonlinear sigma model description of any O3 sigma model. Then when you have spin 1, when you give Lagrangian description and then take care of proper Berry phases and put them together, and Haldane discovered this famous Pontryagin index term, which counts the number of skyrmions that are produced as the spin configurations evolves in time. So it's an integer. It's multiplied by theta, which is 2 pi times the spin of the underlying quantum problem. So if the spin is half integer, then this becomes effective. That is, it interferes, odd number and even number of skyrmion configurations interfere, and you get so-called gapless problem. When it is integer, it doesn't matter, it's irrelevant. So you have gapful spin change. So that's a famous Haldane gap phenomena. Now, this becomes more exciting in 2 + 1 dimension. So soon after our work, Zyroshinsky, Polyakov, and Wigman wrote a beautiful paper in the language of nonlinear sigma model. They said that based on very general ground, you should get a term which is like this. I will explain it. And then they did not derive it from first principle. They pointed out it's allowed and it should have consequences. And then Haldane challenged this and said that a half term doesn't exist when you sum Berry phases. But it turns out Haldane is not correct. In fact, in 2 papers, one paper mine, and then earlier than that, a paper by Danilov, beautifully Danilov shows that you can group Berry phase terms of each spin properly and get a half term. So let me explain what is going on here. This again, the power of gauge theory, how it can distinguish non-trivial spin configurations which are part of the quantum fluctuations. So the idea is the following, that is, you have a plane in which there is this n vector living. This is a sublattice magnetization. So you allow it to evolve in time. So in path integral, you will sum over all possible configurations. So then what Polyakov, Zyroshinsky, Polyakov, and Wigman pointed out was that suppose you create a skyrmion. You all know what a skyrmion is. It's a very simple object. So the spins at infinity are pointing in the north along the positive z axis. At the origin, it's pointing along the negative. So you continuously interpolate. And then there is a circle around the middle in which spins are lying in the xy plane. So spins are up and it's down here. So this can be mapped into an S2, surface area of S2 sphere. So if it completely covers, this is supposed to be a Skyrmion configuration. Exactly, also stereographic projection. Now, then it is a very, very important thing that this Skyrmion carries a notion of chirality, which is not obvious, but however, if you look at this circle where the spin lies in the plane, depending on whether it's a Skyrmion or anti-Skyrmion, it will rotate clockwise or counterclockwise. So that distinguishes. So that basically says that locally these kind of things are positive or negative. So there is a spin chirality here. So what Polyakov and company pointed out was that if you take this Skyrmion and then rotate it adiabatically, the spins will rotate and then collect the phases together, it will give you the spin of the Skyrmion. So they pointed out if the spin of the Skyrmion has to be 1, then you have to have a half term. Then also if you have 2 such Skyrmion, and then if you exchange them, then in this space in which you identify time t equals 0 with time capital T, this will form a knotted loop. So this half term will find out whether there is a loop like this or not. So the gauge theory, because it's interesting, this is where the gauge theory comes. So there is a local constraint, correspondingly there is a topological current. And from this topological current you can draw a vector potential. And this vector potential couples to current, this is a topological, this is a half term. So in Chern-Simons language it looks very simple, but if you want to go to the N language, you'll have to invert J and N, which is very complicated in this equation. So it's messy. Whereas in this language it's very simple, but this is the famous Chern-Simons theory of knots and so on. So it was before Witten's Fields Medal winning work that Polyakov and company did this and did something called framing and got very beautiful results. So gauge theory coming from a very simple spin system throws light on some very unexpected things like winding of curves and how they are knotted among themselves. Okay. So this is one. Now this is a whole field. Yeah. Sorry? It seems like theta can take any value. Right. So the issue is about theta. So Polyakov pointed out, DPW pointed out that this theta for spin-half model is like 2 pi s or some number, I don't remember. So that will make it a fermion. That was the issue. But Haldane said that the half term is not there at all.
So what I meant was, if that's a Chern-Simons term,
yeah.
then the coefficient has to be quantized.
So here it is Born quantized because the theta is a spin of a spin that we start with.
Because I see papers where they argue that theta can be like an intermediate number also. We'll check.
Okay. So that's going beyond this nonlinear sigma model. Suppose you want to describe some general situation called anions. Then you can make theta. I suppose there are Chern-Simons theory in which there are matrices also. There are K matrices. I'm not very familiar with it. But this is a very simple situation. I can give references. So quantum Hall effect is another situation like the spin problem or a strongly correlated problem that we have. Let me just give 2 minutes introduction to the kind of issue that we face as a many-body problem. You have electrons confined to a plane and you apply a very strong magnetic field. So then you know that the spectrum, one electron spectrum density of states, which was constant in 2 dimensions, gets discrete, and this is H cross omega. So you have discrete spectrum, and each level is highly degenerate, and the degeneracy corresponds to the number of flux, quantum flux, that is going through this plane. So that is Landau level problem. Now, in gallium arsenide in various quantum Hall system, what you can do is you can put the chemical potential somewhere in the middle of this level and do some transport measurements. You find remarkable quantization of conductance, Hall conductance particularly. Only E and H comes, nothing else. So these are famous for quantum Hall effect, and there are fractional quantum Hall effect. Integer quantum Hall effect in some sense is very simple, but fractional quantum Hall effect is very very interesting. You have degenerate set of states corresponding to each Landau level. In different bases, you can think of them as like Gaussians localized at different region in the plane for so-called von Neumann lattice, or you can think in terms of Landau states, which are like Newton ring states. Now what happens is you have an electron here, an electron here randomly. There is no one body. These are all eigenstates, so the electrons don't move. So if you put it in a Gaussian state here, it doesn't move. There is another nice neighboring Gaussian state with a phase factor. So they stay put here. But something remarkable happens. What happens is, while one electron kinetic energy is inactive in this submanifold, if we put two-body interaction, electrons become very active. There are off-diagonal matrix elements which hops this electron to another hopping orbital here, for example, to another orbital here. So two-body interaction generates dynamics. So there is a backflow. Exactly like we had before. So things move in a constrained way. So as I am going, I give way to somebody else. So it starts moving like this. So it generates two-body dynamics. Now I can do exactly the same thing that I did. I take the two-body term and factorize it. I get a hopping accompanied by a Hartree-Fock potential, which can be written in terms of Peierls factor. So I generate dynamical gauge fields. It's as simple as that. So in a constrained situation, you have to cooperate and move together. So you give me a phase, I will give you a phase. We'll organize it, and at the end we'll get Nobel Prize. Very beautiful, organization into Laughlin wave function. So that is the kind of thing that goes on in fractional quantum Hall effect. And what you find is remarkable Chern-Simons theory coming in, very complicated with K matrices and so on. Zhao Wen has done a lot of work on this. He describes it beautifully in his book. So,
you said that if they're not interacting, they just sit where they are.
There, yeah.
And you turn on the Coulomb interaction and they start moving.
Exactly, the Coulomb interaction, exactly, just Coulomb interaction.
It's related to this very classical phenomenon called E cross B drift. Something which is just sitting in an orbit. But if you put an electric field on it, it moves in a direction perpendicular to both the electric field and the magnet. Right?
Exactly, so I'm...
Your picture suggested
Precisely.
if they exert an electric field on each other.
Yeah.
I was just wondering. Anyway.
In fact, maybe what you are saying can be... So, no, he's talking about how the two electrons can be interpreted in that language. So maybe to illustrate that, so I take the Landau level problem and put two electrons, just two electrons. In the absence of Coulomb interaction, they sit wherever they are. Now I put Coulomb interaction and Laughlin solved that problem. That wave function has a very simple form. So Z is x plus Iy. So these are all the coordinates of the two electrons in the plane.
Is this a solution or is it an ansatz?
Solution, exact solution. In fact,
For interaction is not appearing explicitly.
exactly, that's another interesting point. Because I'm in the lowest Landau level, interaction, so this is the quantum number of various bound states. So in fact, Laughlin solved the quantum Hall effect problem the way Onsager solved the Ising model problem. So he solved two electron problem. He found this eigenfunction. It can be exactly found. So he solved three electron problem. He solved it numerically and he made an ansatz, which is this. It had 99% overlap with his numerical work. Then he generalized it to n electron. So this tells you what you are saying. This is saying that these two electrons start orbiting around each other with angular momentum m. In the absence of interaction, these states are not the relevant eigenstates. And the energy also starts depending on this m, in fact, that energy is called Haldane pseudopotential. Okay, very good. Exactly, it's a mean field on such. Then you can go beyond mean field through the gauge field. So you can take quantum Hall problem and write down the Hamiltonian in terms of this electron operators in the Landau basis. You have off-diagonal terms, do a mean field ansatz, then solve. Sorry? No, so I'm rationalizing the meaning of the mean field. I'm saying that we did a mean field theory, we got Hartree-Fock vector potential. When you solve the problem, exactly similar thing happens. So the two particles goes around each other. And the potential, the Coulomb potential is being the Hamilton. So you're going along with potentials. Hamilton's equation will tell you that you go along with energy space.
That's nice, yeah. The guiding center is actually constitute a phase space.
Yeah.
X and Y coordinates of the guiding center don't come.
Thanks for the remark. So as Rajaram pointed out, when you take positions of two electrons and project it into lowest Landau level, then they are called guiding centers. The X and Y component do not commute. So all the things are because of that. Yeah, okay. Yeah, exactly. So there is a magnetic length which appears as a non-commutativity parameter, so-called magnetic length. Okay. Now, the rest of the time, I will see, with great difficulty we were doing this. Meanwhile, Kitaev came up with a series of unpublished papers. Often they were in some ITP lecture notes. And now I have found out this like a theorem. Kitaev models are extremely friendly ones. Now we talk about Hubbard Model only, but the answers, even though Elliott-Leib is a good friendly person, his solutions are not. Whereas we will see the Kitaev models, I don't know about Kitaev himself, I have seen him from a distance, models are very friendly. I'm told he is a very humble and friendly man. Okay.
He
So
came to IISc. Kitaev visited IISc before he did all this famous work for a meeting with Rahul Pandit.
Oh, I see. He and Levito were colleagues and they were doing step model. I see, okay. So now I'm going to do this. So there are some young graduate students in the audience and young friends. If you have not studied Kitaev model, please study them because each will take just 1 hour to master whatever he has said. Then you have the rest of the time to go beyond. That is the power of Kitaev's models. Okay. So here is a spin model, which is going to tell you about gauge theory of dislocations after a few steps. So what do I have? I have a square lattice and I put spin variables on the bonds at the center of the bond, not on the sides. Okay, so I have a very simple square lattice spin system. Then I write down a Hamiltonian which contains product of 4 spins at every vertex. That is, if I take this vertex, there are 4 spins along the 4 arms. So it's like a cross. What do? I take the X component of spins in this star, which is a 4 spin term. Then I go up and look at any Planck weight, and there are spins at the bonds. I take the Y component, Z component. So it's a sum of 4 spin terms. In the vertices, there X component up here and here Y component up here. So you may think that they don't commute. Miraculously they commute because if you just do the theory, mathematics is very simple. Whenever 2 adjacent Planck weight and cross meet, then there are same spin appears twice. So the product of 2 anti-commuting things commute. It's as simple as that. So these terms commute. So it's a commuting classical looking Hamiltonian, but it contains some very deep quantum physics and topology. And Kitaev discovered it in the context of error correcting codes in quantum computer. I will not go into that. So the ground state is very simple, in which this A take value +1 everywhere, B takes value +1 everywhere. And you can convince yourself there are many spin configurations for which it is true. So you can, for example, write down one such configuration, one such ground state as a coherent superposition about all those spins. So it's like a liquid of spins. Then I want to create an excitation. What will I do? I can imagine a situation in which this product, the green P, is negative, or this is negative. Then I call that as an excited state, and you can convince yourself that if I create that, it won't move. There is no dynamics in this problem at all. There are just configurations. Then I call this electric and vortex, and something remarkable happens, which he showed. That if I take this excited states that I have created and adiabatically transport them around, I get this very unusual, non-trivial mutual statistics. This is where quantum physics come. Because in solving the problem in terms of eigenvalues, there is no quantum mechanics. Because everything commutes, I have ordered the states. But if I create an excited state and adiabatically transport them, there is some communication between them, some entanglement. So it gives you a phase factor -1. So this is a first instance where in a simple model, there is a mutual statistics between these two different objects, which is -1. For example, fermions and bosons are these. So they are called anions now. Okay, so this has been extensively studied in terms of Chern-Simons theory and so on, and in terms of topological degeneracy. I will not go into the details, but just to point out that this is for the beginning of a model called the Fracton model, and this is a good reference to it by Anand Kishore and his company. Okay, what do I do? Apparently, this gentleman Ha was also interested in error correcting, building error correcting codes. If I have time, I will tell about error correcting a little later. He constructed a model. In fact, I tell my student friends that if you have time, please construct your own Kitaev model or X-cube model. It is possible because number of lattices are in plenty. You will learn things at the same time you will enjoy. There are new things that you may discover. The way Ha discovered so-called fracton. So this is Vijay Sagar and Liang Fu. Ha had a more complicated model. This is a simplified version. So what you do is you take a cubic lattice and put spins at the bonds as before, and then define term A, which is a product of 12 spins. So previously we had 4 spin product, now we have 12 spins. So I'm not going to say that this is an effective Hamiltonian of some spin system, but it's a model. Okay, so you take the X component and do it. Then come to this, and here if you take any site in the cubic lattice, there are 4 planes, X, Y, Y is in 3 planes. Take the corresponding 4 spins and their Z component. So you have X, here it's X component, it's Z component, that's it. As before, they are commuting. Then what do you do? Now let's create excited states. How do you create excited state? Take one of the ground state configuration in which AC is 1 and B is 1 everywhere. Then I flip one spin. You can convince yourself in the process, it will create 4 boxes which are unhappy, where A is minus. Now you can flip more spins and then you can move them apart. So the way it appears is these defects we are able to move kinematically by flipping spins only in the plane. So that's why they are called fractons. They have fractional dynamics in only one direction. And then you can do several things. And you can do exchange statistics. So this is again a very simple model. Now if you try to do low energy physics of this and put gauge theory, apparently you get 4-rank tensor gauge theory, which is the talk that I heard last month. So a very simple quantum model gives a connection at some low energy physics to elasticity theory. Okay. Having said that, let me spend the rest of 10-15 minutes about this very non-trivial, but at the same time solvable Kitaev model. Historically, Ashwin was visiting me. He's from Bangalore. So once he visited me at Mansions when I was a graduate student. So he told me about Kitaev model. I didn't, it was there in the internet, in Santa Barbara lecture notes. I didn't appreciate what was going on. Then Ashwin told me, Baskaran, it's your RBB mean field theory. Then I woke up. Then what I found was, Kitaev has taken this very beautiful model, I don't know how he thought about it, and used a trick which we did, namely mean field theory, and it gives exact solution. And all the dreams of gauge fields and the pseudo-Fermi and everything comes in a beautiful way, in an exact fashion. And you can do many, many things with this. So let me say, so this is a model. What you do is you take a honeycomb lattice, you have spins on the sides. So you have now three colored sides, three bonds going down called blue bond, red bond, and green bond. Now what you do is along the direction 1 and 2, then you put interaction spin components XX. Along the y direction you put YY and then ZZ, XYZ. So terms wise it looks Ising model, but the coordinate is rotated, and remarkably the terms are not commuting. It's genuinely quantum. So you can't diagonalize it by just looking at it. So this is a quantum problem because these boxes don't commute. So you have to solve it. So it looks like 1/3 of Heisenberg model, because I can take Heisenberg model in which all the three components will be there. For example, drop X, Y and Z component along this link, and drop X and Z component along this link, and drop X and Y component along that link. So it's 1/3 of Heisenberg model. And it is exactly solvable, which has a very rich spin liquid physics. One more thing he observed, sorry for this, Rajaram, the same question mark which plagued you is coming here. I don't know, there's a question mark, right? Okay, so this is supposed to be a product. So if we take the Planck weight and take the product of the spin with the convention that you take the sign corresponding to the outgoing bond, you get a flux operator, and that commutes to the Hamiltonian, and that commute among themselves. So this Hamiltonian has some n number of conserved quantities, but still it has dynamics, as I will show. So in particular, the square of BP is 1. There should be a square here. So that means its eigenvalue is plus or minus 1. So that immediately breaks my Hilbert space. There are two n sides. So the Hilbert space dimension is 2n, 2 to the power of 2n, into Hilbert space of various sectors. Now we are going to see, again, a miracle that the problem in every sector is solvable as free fermion problem. Sorry. This is some not that bad. So Kitaev used Majorana fermions, whereas we used physical electrons, so you can form a linear combinations. I will not go into the detail. What is the observation of following? Suppose you take a complex Dirac fermion, which is complex, write it as a real and imaginary part. Then they have this anti-commutation relation. Further, the squares of them are 1. Nominally, you can say, if the Hilbert space dimension of this Fermi oscillator is 2, the Hilbert space dimension of this real and imaginary part, so-called Majorana fermion, are square root of 2 and square root of 2, nominally. In fact, it's more than nominal, because when you solve two-channel Kondo problem and many other situations, you get a square root of 2 Hilbert space locally, as you can get from specific heat measurement in the entropy. Okay, that's a very, I will not go into the detail. If there is a question, I will answer that. So what Kitaev does is, he introduces a representation for the Pauli spin variables in terms of, where is that? Yeah, that's right. So the X or Y or Z component can be written in terms of products of two Majorana fermion, a scalar Majorana fermion and a vector Majorana fermion. If you put that, they still obey this spin anti-commutation relation. However, because there are 4 Majorana fermion, the Hilbert space is 4-dimensional. Unlike a Pauli spin operator, the Hilbert space is 2-dimensional. So you have to have a restriction. That restriction says that operate with this operator. If it is +1, it isolates 2 states. If it is -1, it isolates 2 minus states. So these are local constraints, which in this analogy, so it's as simple as this. So this just writing spin operated in terms of physical electron operators in terms of this 4 Majorana group. Some remarkable thing happens. Now you substitute it in the Hamiltonian. You have this scalar Majorana fermion, which is the first one, and the vector fellow. They factorize into Ci, Cj, and these 2 vector Majorana fermion become like this. And in a remarkable way, this vector Majorana product at every link commute with the Hamiltonian and among themselves. So what Kitaev has done is he did Hartree-Fock factorization, but the object that he factored is a classical object. It doesn't have quantum fluctuation. So Hartree-Fock theory becomes exact. Now if you look at it carefully, you have generated Z2 gauge fields. Because you can take this Uij and multiply it by tau I, tau j, which corresponds to some local gauge transformation, with tau I equal to plus or minus 1. Then in a given sector, I have this Hamiltonian. Now I have to say what is the connection of this BP operator with this Uij. It's very easy to show that in the BP operator, a product of 6 spin operators, substitute them in terms of this Majorana fermion variable, it becomes a product of the 6 link variables in the hexagon. So that's a Wilson loop. So if I call this 1, 2, 3, 4, 5, 6, the BP operator is sigma 1 Z, sigma 2 X, and so on. When I substitute after this manipulation, it becomes tau 1, 2, what is U12, U2, 3, U5, U7. So now they combine together, gives you link. So this is basically Wilson loop of Z2 gauge fields around this link. So in a very simple way, I have converted the problem of spin in a particular BP sector into Majorana fermions freely hopping in this static background gauge field. So I may choose use to be all +1, for example. Then the product will be always 1. And that corresponds to the lowest energy sector in the whole problem. That is due to some theorem called Leib's theorem.
Mr. Baskaran, we have 10 minutes, including questions.
Including questions. So I will stop in a few minutes, So what has happened is, Hilbert space is getting fragmented beautifully, but now in a very physical way, in a gauge way. The physical dimension of Hilbert space, as I said, is 2 to the power of 2n. Enlarged Hilbert space has dimension 4 to the power of 2n. Now, what this has done is introduce this gauge redundancy. It splits this into 2 to the power of 2n gauge copies of 2 to the power of 2n states. So each box is a physical state, and they are all gauge copies. And what is remarkable in this problem is the spectrum are identical in all gauge copies. So it's a very beautiful gauge theory in which everything is exact and very simple, countable because it's discrete. So how do we say that every sector has the same spectrum? I do a gauge transformation. I start with, say, given Uij and do this transformation, and I generate all these corresponding vectors here. And the spectrum are identical because gauge invariant object is a product around a loop. So now let's look at a simple case in which the flux is 1 at every sector. So this is free fermion, Majorana fermion hopping on it. It can be solved, which is what Kitaev solved. What we find is the Brillouin zone in so-called Dirac cones. So it's half of graphene in the sense honeycomb lattice is the lattice of a graphene, but I have, instead of complex fermions hopping, I have real fermion hopping. solve the problem by Fourier transformation and Bogoliubov transformations, I get physical fermions running around with this dispersion, and there are only particles, no antiparticles, because they got identified. So the dream of RVB theory is realized in this beautiful model that you have so-called pseudo-fermions, which is there in a spin system. There are no fermions in the problem because they are just spins. They have some anisotropic interaction. But at the end of the day, I have gotten a spectrum of propagating fermions. And this has been confirmed in neutron scattering experiments in Kitaev compound discovered by Kaliulin and Jacqueline. There are some real systems. So I always tell friends that if you solve any model and exactly nature is always kind, you will find some way somebody confirming it. Okay, since the time is up, let me see, what do I have? So I have several things. I think it's better time to stop here. And also just to point out that the Hamiltonian that I had, Kitaev Hamiltonian, has 3 parameters, Jx, Jy, and Jz. So you can think about a phase diagram involving all these 3. And it's remarkably gapless in this region. We are talking about the center here. And as you move towards these edges, the Dirac cone move, and they annihilate each other and produce a gap. Then if you go to this extreme, you get the original Kitaev story code Hamiltonian. It's amazing that Kitaev discovered a particular case here, and then got this general case here. And then you can apply magnetic field here, and then create anions or Majorana fermions and show unusual exchange statistics and so on. So with that, let me summarize by saying that gauge theory is as old as Maxwell, but then later in the last century, it appeared in different contexts: dislocation theory, superfluid helium, liquid crystals, and quantum spin liquid and quantum Hall effect, and now this Fracton, a variety of contexts. And they seem to be offering solutions to strongly correlated problems, because strongly correlated problems are many, at least some of them can be understood in terms of these emergent gauge fields. So many things are still not very clear, they are mysterious, but the fact is they work. So I gave you some sketchy discussion about it, and then if you take this Kitaev model, any of these Kitaev models, starting with honeycomb lattice, it's very easy to work out in 10 minutes, because I have told you the basic thing. So you can write, there are many things to be done. It's like a gold mine. Thank you very much.